Now, in the case of transverse susceptibility, the magnetic field is applied perpendicular to the sublattice magnetizations M sub A and M sub B. And when that happens, as you can see, the magnetizations of the two sublattices will tilt from the easy axis by an angle alpha. And if the magnetic field is applied in the positive z direction, you can see that the magnetizations, when they tilt by an angle alpha, also the PHYS molecular fields they will feel will be tilting by an angle alpha. So this angle alpha will be the same for the PHYS molecular fields. So let's look at this carefully. I have the A sublattice magnetization tilted by an angle alpha, and it feels a PHYS molecular field HWA, PHYS molecular field acting on A, is gamma times MB. And that is, remember, actually pointing in opposite direction to magnetization of the B sublattice, which itself is tilted by an angle alpha. Therefore, the PHYS molecular field acting on A sublattice is tilted as well. And similarly, for the B sublattice, it's tilted magnetization by an angle alpha, but feels a PHYS molecular field acting on the B sublattice, which is minus gamma times MA vector, so magnitude gamma times MA, pointing at an angle alpha with respect to the easy axis as well. So when is the equilibrium reached? When the applied field H matches that of the PHYS molecular field, total PHYS molecular field, there will be no need for rotation because the net magnetic field acting on the spin sublattices will be 0. So we see that the applied field H rotates sublattice magnetizations M sub A and M sub B by an angle alpha. At equilibrium, we will have the PHYS molecular field, total PHYS molecular field acting on the sublattice magnetizations equal to the applied magnetic field H. When this condition is satisfied, no need to rotate further because the net magnetic field will be 0. So we don't need to rotate further. Now we have the following relationship between magnetizations of A and B sublattices. In absolute value, they are the same. So the magnitude of the magnetizations is the same. And we also have the PHYS molecular field acting on A magnitude is equal to the PHYS molecular field magnitude acting on B, which is equal to gamma times MA or gamma times MB. It's the same thing. Then if I write the total PHYS molecular field, as you can see, I have the component of PHYS molecular field acting on B on the z-axis, which will be gamma MA sine alpha. The component of the PHYS molecular field acting on A sublattice on the z-axis, gamma MB sine alpha. So this is gamma MA sine alpha plus gamma MB sine alpha, which will be equal to 2 gamma MA sine alpha because MA equals MB. And for the net magnetization, I have MB sine alpha plus MA sine alpha on the z-axis. So MB sine alpha plus MA sine alpha. So this will be equal to 2MA sine alpha. Therefore, I see that the PHYS molecular field HW, which was equal to 2 gamma MA sine alpha, is actually gamma times the net magnetization M net, and it is equal to the applied magnetic field at equilibrium. This is the condition. So we find that the transverse susceptibility, which is the net magnetization that we are measuring divided by the applied magnetic field, will be equal to 1 over gamma. Now, recall that from the PHYS theory of antiferromagnetism, we have a relationship here. Theta is equal to the Néel temperature, theta is C prime gamma, and C is 2C prime. So if we use these relationships, C prime gamma is equal to theta, C is equal to 2C prime. So I have gamma is equal to theta divided by C prime, or since C prime is C over 2, 2 theta divided by C. Therefore, I can write the transverse susceptibility as C divided by 2 theta, but since we have this theta approximately equal to the Néel temperature, remember it was approximate because we were neglecting the next nearest neighbor interactions in the PHYS theory. So we have the transverse susceptibility given by C divided by approximately twice the Néel temperature. So the transverse susceptibility is inversely proportional to the Néel temperature, we can say. And it's a constant for a given material. So the transverse susceptibility is a constant below the Néel temperature. It has no temperature dependence. The susceptibility, transverse susceptibility, is not a function of temperature. It's a constant. It's controlled by the Néel temperature of the antiferromagnet. Okay, so in summary, when we apply the magnetic field perpendicular to the sublattice magnetizations, the equilibrium condition is reached when the PHYS molecular field acting on the sublattices is balanced by the applied magnetic field, so that the net field acting on the sublattices will be zero and no need for rotation. When we write this condition, we find that the PHYS molecular field must be equal to gamma times the net magnetization, which is the applied magnetic field at equilibrium. And so transverse susceptibility is 1 over gamma, or C divided by twice the Néel temperature, which is a constant, so it's not a function of temperature.